Hey girls, in today's lesson I want to go through the requirements for this standard and just make a start with a bit of revision from last year. So this standard obviously is 91393, Demonstrate Understanding of Oxidation Reduction Processes, and it's a 3-credit internal. Okay, so this standard includes some revision from last year and also builds on what we've done last year, particularly considering how electricity can be generated from a redox reaction and how it can be used to force a non-spontaneous redox reaction to occur. So that process is called electrolysis, and we're going to go through those in some detail. By the time we get to the end of this standard, what we're looking at is a comparison between spontaneous and non-spontaneous redox reactions. So to make a start, we need to start off by reviewing the principles of redox reactions. So what did we learn last year in redox? What is a redox reaction? How can we identify what's been oxidized and reduced? And what are oxidation numbers and how do we calculate them or determine them? So redox reactions. A redox reaction is simply where one species is oxidized, it loses electrons, and the other is reduced, it gains electrons. So both oxidation and reduction have to happen together. You never get them happening on their own. You can't have an oxidation reaction without a reduction reaction, and vice versa. We know that it's happening overall, you're going to have a transfer of electrons from one species to the next. So how can we identify what's oxidation and what's reduction? Because that is a key part of the standard still. If you can't identify what's been oxidized and what's been reduced, how do you even know that a redox reaction is happening? So oxidation is gain of oxygen. That's the simplest definition of it. You can also think of it as an increase in the number of bonds to an oxygen. So going from a single bond to an oxygen to a double bond to an oxygen would also count as oxidation. Often you get loss of hydrogen. You don't always get oxygen or hydrogen changing, mind you, but you always have a loss of electrons for oxidation, which means that you will see the electrons on the right-hand side of your half equation. Okay, and the oxidation number will increase. More about oxidation number in a minute. Reduction, of course, is the absolute reverse. So a removal of oxygen or a reduction in bonds to an oxygen. Gain of hydrogen, again, neither oxygen nor hydrogen has to be involved, but they may be involved. You get a gain of electrons, which means your electrons are on the left-hand side of your equation. They are reactants in your reaction. And you get a decrease in your oxidation number. So let's have a look at a couple of examples of this. Okay. First example, I'll just get that out of the way for a sec. Okay, so the first example, we have sulfur dioxide turning into sulfate. Now, you haven't got a balanced half equation there. You could balance it to figure out where the electrons go. You could work out the oxidation numbers. But in the meantime, you can also look at it and go, well, we've gone from having 2 oxygens in our sulfur dioxide to having 4 oxygens in our sulfate. We've had a net gain in oxygen. Therefore, this must be oxidation. Our second example, iron 2 plus turning into iron 3 plus. That's written as a half equation. You can see the electrons are on the right-hand side of that half equation. Therefore, electrons are being lost. It must be an oxidation reaction. You can also look at the oxidation number, the charge, here on the on the ions. For a simple ion like Fe2 plus or Fe3 plus, you can look at that. And you can say, well, the charge has increased. Therefore, the oxidation number has increased of the ion, and that must be another way to figure out its oxidation. If we look at the third example, dichromate turning into chromium 3 plus. In this case, we have lost oxygen. We've gone from having 7 oxygens on the left-hand side of the equation, or 3.5 oxygens per chromium, if you want to think of it that way, to having no oxygens on the right-hand side. That net loss of oxygen means it must be considered reduction. Now, in this case, because the dichromate is a polyatomic ion, you can't just look at the charge and say it's gone from 2- to 3+, because that will give you a completely wrong answer. It is completely inaccurate. Okay, and the last example we've got down there is ethanol turning into ethanal. Now, we haven't covered aldehydes yet. That'll be something we'll look forward to in organic. But ethanal has a double bonded oxygen. Ethanol has a single bonded oxygen. So we are increasing the bonds to our oxygen. That makes it oxidation. We are also losing hydrogens. We're going from 6 hydrogens on the left-hand side to 4 hydrogens on the right-hand side. So that must also indicate oxidation. Okay. Now, I've mentioned oxidation number a couple of times here, but oxidation number is something we need to go through a little bit more detail and just become clear on. Okay, so determining the oxidation number is the best and most accurate way to determine whether oxidation or reduction has occurred. But the important thing to remember, and the thing people keep screwing up, is that oxidation number always refers to a particular element. Even if you're looking at a compound or a polyatomic ion, you have to determine the oxidation number for every single element within that substance. Okay, you can't say the oxidation number of sulfur dioxide is this, or the oxidation number of the carbonate ion is this, because that's not correct. You've got the oxidation number of the carbon in the carbonate ion and the oxidation number of the oxygen in the carbonate ion. You have to work those out separately. There are, of course, some rules. They're not simple, but they are fairly straightforward. Okay, so the first one is that the oxidation number for a pure element is always 0. So if you have an elemental substance, you know, you've got some iron metal, you've got some hydrogen gas, those sorts of things, the oxidation number for those substances is always going to be 0. If you have a simple element, a simple ion, a simple monoatomic ion, like we've got the sodium ion, the chloride ion, the aluminium ion, the zinc ion, the copper ion, you get the idea, then the oxidation number for those simple ions is always the charge on that ion. Where it gets complicated is when we have compounds and polyatomic ions. So these are things with more than one type of element present, because at that point we can't use a simple, you know, here, let's look at it and there's the answer. We have to actually calculate it. Okay, but there are a couple of things we can use to help us. The first thing is that when we are in a compound or a polyatomic ion, oxygen always has an oxidation number of -2, except for when we have a peroxide, in which case the oxidation number is -1. And you come across that with hydrogen peroxide particularly. Hydrogen always has an oxidation number of +1, except when we're in a metal hydride, in which case it's -1. And the sum of the oxidation numbers, in other words, if you add up the oxidation number of every single atom in the molecule, or compound or polyatomic ion, then the sum of those oxidation numbers will add up to 0 for a compound, or the charge on the ion for a polyatomic ion. So let's have a look at some examples of that. The first line, we have oxygen gas, nitrogen gas, chlorine gas, iron metal, and copper metal. They are all pure elements, therefore all of their oxidation numbers are 0. So the oxidation number of oxygen in O2 is 0. The oxidation number of iron in Fe, when there's nothing else written there, is 0. The next line down, we have some simple monoatomic ions. Those are ions with only one atom involved. We have sodium, copper, oxygen, and fluorine. And for each of those ions, the charge on the ion is the oxidation number of that substance or species. So the oxidation number of sodium is +1. The oxidation number of copper in copper 2+ is 2+. The oxidation number of oxygen in the oxide ion is 2-. The oxidation number of fluorine in the fluoride ion is F-. So those are the easy ones. The last two are slightly trickier. They are related. So let's have a look at them. First, we have sulfur dioxide. So in the sulfur dioxide molecule, we have 3 atoms, 1 sulfur atom and 2 oxygen atoms. Don't forget that there's 2 oxygen atoms there, please. Okay, we know from the rules that each oxygen atom has an oxidation number of -2. There are 2 of them, so 2 minus 2s is -4. But each one is only -2. Okay, the oxygen doesn't have an oxidation number of -4. Each oxygen has an oxidation number of -2. That might sound like I'm being really picky, but it's really important. The sum of the oxidation numbers must equal 0. So the oxidation number of sulfur plus the oxidation numbers of the 2 oxygen atoms must add together to equal 0. We know it's 0 because there's no charge written here on the ion, on the molecule. So something -2 minus 2 equals 0. Therefore, the oxidation number on the sulfur must be +4, because +4 minus 2 equals 0. You can work it out through some simple algebra if you need to. And the last example, the sulfate ion, works in much the same way, except this time the oxidation numbers of the sulfur and the 4 oxygen atoms has to equal -2 because that is the charge on the ion. So sulfur minus the oxidation numbers of 4 oxygens, each at -2, must equal -2. So in other words, we could set it up as an algebra equation, something minus, or something plus, 4 times -2 equals -2. The sulfur must have an oxidation number of +6. Because +6 minus 2 minus 2 minus 2 minus 2 is going to give you an overall answer of -2. Okay, I think that's more than enough to continue on with today. We're going to work on these in class. There are some practice examples online for you already if you want to start working on those, but we will have time for consideration and discussion of this in class. Please do review this video, have a look at the bits that didn't make sense to you, write down some questions to bring to class. If it all seems perfectly sensible and logical, then I guess I've done my job well today. I will see you all tomorrow. Have a great day. Hope this makes sense. Catch you later.